Welcome back to the classroom. My name is Mr. Wong. Today we'll be going through an exam question for kinematics. As you can see here with this diagram, we have a table of results down here. And we're performing an experiment where a trolley is rolled from rest, which means our starting velocity is 0, down an inclined plane. The time for the trolley to roll various distance was measured using a light gate. A light gate is what we can call a motion sensor. It detects the speeds and times as an object passes it. So we went through 6 rundowns. These are the results that we have here. And let's have a look at what we need to do with these results. So the very first question, it says complete a graph of the results using the axes provided. So these are numbers. Let's try and scroll out here. We might be able to show for better representation. Okay. All right. So what we have here on this left-hand side here, we have the data points for the distance between the light gates, how we increase it, and we also have the time taken for the trolley to roll down. Now, the thing I want to kind of stress is we are dealing with time roll down squared. Okay, so it's seconds squared, not seconds. There are some implications later on in the question, which we will talk about. So in this question, it says complete the graph of results using the axes provided. What we need to firstly work out is which axis is for what. So based on the numbers that we have, on this side, this is time squared. So I'm going to write time, whoops, I'll just redo that. So on this side, I am going to write time squared here. Just pick my color again. So we have time squared or seconds squared. Whoops, it's a little bit funky with the writing pad and the borders, but we should be able to pull through this one. So time squared, seconds squared, like so. And then on this side, we have distance. Make sure you label the correct axes and also include the units. The next part is just to graph the data points here onto my table here. Okay, so I'll do that very quickly. Okay, so we've plotted the graph, and what we need to now do is a line of best fit. So to do that, I'm going to draw it with a different colored pen. I just want to highlight the data points that we have here. Clearly, this one is quite out of sorts with, or the actual point seems like an outlier to these data points here. Now, when you're drawing your line of best fit, you don't have to include it when drawing your line of best fit. Instead, you can just circle it here, comment, this is my outlier, Mr. Examiner, and at least the person marking the paper will know that you didn't consider this in your line of best fit. So line of best fit should be a nice straight line or curved line through the dots of your data points. So that's what I'm going to do. Hopefully I don't stuff it up. So sort of straight line. Actually, what I will do, so I cheated a little bit here. I used the shapes to do my line of best fit instead. Okay, alrighty. So line of best fit and all sorted. You could even find the gradient value at this case, but I don't think they're asking for that, so we can leave that as it is. Next one, it says use the information in your graph to determine the acceleration of the trolley down the incline. So let's actually look at what the gradient we have here. So the gradient we have here is t squared over displacement. Okay, t squared over displacement. So let's have a look at the formula. So we have displacement equals to initial velocity times time, half at squared. This is the form we're dealing with here. As you can see, if you look at the other kinematics equations we have, v equals to u plus a, and then v squared equals to u squared plus a to as. You can see none of these equations actually give us t squared. And obviously this one at the top here doesn't give us displacement. So this is the most logical equation that we have. Let's try and rearrange this equation to get to this point here. So I know that u is 0 because we have a 0 initial velocity. Okay, so it will be s equals to half at squared. Rearrange the equation, so I get 2s over t squared equals to acceleration. So this formula is that. Now, what we can see here with our gradient line is it's 2 squared over s. So what I can do is I'll flip everything around first. It'll be t squared over 2s equals to 1 over a. Then I'll just push the 2 out. There is that value there. So what we actually have, t squared over s, is actually the inverse of the gradient value is the inverse of the half of 1 over acceleration. Okay, so let's work out what the gradient value is. That needs to be any point on your gradient line. So let's pick this line here and this dot right up here. Okay, so this point is about, let's say it's about, I don't know, 12. We've gone to just touching 0.05. And over here, we are at the 61 mark. Around-ish so, and we've just hit the 0.25 as our y component here. Okay, so let's find our gradient, which is this t squared over s. I'll do this in a different color, and I'll also zoom back into the question so we have a bit more space to write it all. Well, actually, we'll leave it as it is. Okay, so to find the gradient value here, that would be 0.25 minus 0.05 here over 61 minus 12. Remember, it's y2 minus y1 over x2 minus x1. And on my calculator, it's a very small decimal point, but they actually give it to you in a nice fraction. I'm just going to leave it like this first, 1 over 245, because I'm going to end up inversing this anyways. Okay, so this is the arrangement we have. For the sake of my calculation, I'm going to use this equation here. So it's going to be 2 times, and I substitute this value here. So S that. So it would be the inverse of this part here. As you can see, this part of my fraction is the inverse, or what we can say is the opposite of this part here. So if I substitute the value I got here into here and inverse it, I should be able to find my value for acceleration. Okay, so zoom back in here, 2 times 1 over 245 inversed acceleration. Okay, so I just got back into our gradient value. There's a little correction I need to make here. And it's to do with this bottom part here. So I misread the question a little bit, not by much. I wrote distance, the units for distance was meters. It's actually centimeters. So please don't be like I did here and read it wrong. So that's centimeters. So I need to convert all these values into meters. Okay, just keep that in mind. You could, for example, write meters and then say 10 times the power of minus 2 to get your right units down here. So what I wrote here where I said 12 is actually 0.12. And when I wrote 61 here, it's actually 0.61 here. So it would be 0.61 minus 0.12. Okay, and then let's just do this again. Okay, and I get a nice fraction of 20 over 49, not the 1 over 245. So I'm going to plug this back into the equation. So it is 20 over 49. And so let's look at what our acceleration value is now. So we get an acceleration value of 4.9 meters per second squared. So that's a lot more reasonable. In the original one, I got 490 meters per second squared, which is incredibly high for a trolley, obviously. So this is how you do the question here. As you can see, this is just my way of solving through the gradient value. Instead of using, substituting my gradient into this equation, I just did the inverse into this equation. An alternative way you could do it is when you do the Y2, the rise and run, you can reverse that construction as well in that explanation. Okay, so that's how you go through this equation or this question here. Hopefully you found it useful, and apologies for the little error on my part for not seeing centimeters. But the process is correct, and hopefully, as you can see, the important part is knowing the procedure, and then obviously you can then backtrack from there. So again, have a wonderful day, and I hope you found this video useful. Like it and subscribe.